So as we begin to prepare to start our first unit, it's good to recap a little bit of some important things from Calculus AB that are going to overlap, especially with this first unit. And being that this first unit is all about approximations, the way we do a linear approximation, if that sounds familiar to you, is essentially writing the equation of a tangent line. Now, while the equation of a tangent line is based off of point-slope form, y minus y1 equals mx minus x1, if you remember with a tangent line, there are, like for example, the slope of the tangent line specifically is the derivative value at whatever location you are finding the tangent at. So we had kind of developed this into a model called L of x. Again, we call this the linear approximation. And to remind you of that model from last year, we would oftentimes write it as f of a plus f prime of a times x minus a. And again, just to remind you where that comes from, technically, this is the y-coordinate at the point that you're actually like finding the tangent. This is the derivative at that specific point. And then this is the like x value of where you're ever, where you're creating that location. So basically all you need to know is what's the derivative, what's the original y value, and what is the x value of the location where you're making a tangent line. So if you take a look at question number 1, it says use the above model to write the equation of the line tangent to each function at the provided coordinate or x value. So technically this function, I'm going to think of this as f of x equals x squared minus 3. So what do I need? I need to know what is the f of 2. Thankfully, in this problem, it's actually given to me that f of 2 is 1, so I don't actually have to go calculate it. But if I did, I would just have to plug in y squared minus 3. Just to kind of recap a little bit of some stuff that might help you in regards to using the calculator, if you go to y equals and you type in x squared minus 3 as your y1 function, when I now go back to my regular calculation screen, if I wanted the f of 2, that's another way of saying the y1 of 2, I would do alpha trace, and it brings up a list of the y functions. y1 is the one I'm working with. You have to type it in function notation, and you can see that I, again, get the same y value as was given to me in this point. Okay, so that's mainly for situations where they didn't give you the whole coordinate pair. So what is my a value in this case? I should have pointed out a is 2. It's the x coordinate of whatever location you're finding the tangent at. Okay, and then the last thing you need is what is f prime of 2. So we need to know first actually what is f prime of x. Using our regular derivative rules, so again, you might have to go back over these if you're a little rusty. Derivative of x squared minus 3 becomes 2x, and obviously 3 becomes 0 because the derivative of a constant is 0. So now I need f prime of 2, which comes out to be 2 times 2, or 4. Okay, so what am I going to need? I need the a value, which is 2. I need f of 2, which is 1, and I need f prime of 2, which is 4. So let me just first write this out in general. L of x equals f of 2, okay, because your a value is 2, plus f prime of 2 times x minus 2. And you're going to leave x as x because the idea is you want something that is a function of x so that you could eventually use this to calculate certain things along this tangent line. So f of 2, again, according to the point we were given, is 1. F prime of 2 we calculated to be 4, and then x minus 2 stays in parentheses, and this ends up becoming the tangent line to this function at this specific point. Okay, so kind of keeping up with the same model, let's take a look at question number 2. So once again, we're fortunate that we are given that a equals 4. We already know that f of a equals 2 because that's given to us. So we need to figure out what is the f prime of x function. So again, if you think in this case of f of x as x to the 1/2, that way when we do the power rule to find f prime of x, you drop your power down in front, subtract 1 from your power, which is another way of doing 1 over 2 radical x. So I want the f prime of 4, okay, because again, my a value is 4. So I'm going to plug in 1 over 2 radical 4 is 1 over 2 times 2, or 1/4. Okay, so my general model is L of x equals f of 4, because that's my a value, plus f prime of 4 times x minus 4. So as I start to plug in, I'll have L of x equals f of 4 was given to me as 2. We calculated f prime of 4 to be 1/4, and then x minus 4 just stays like that in parentheses, and that is now the equation of my tangent line. Okay, just again to do a little bit of recap with derivative rules. The third example involves just like a slightly harder derivative, but all the concept is mostly the same. We're being asked to write the equation of the tangent line at x equals 1. That's a fancy way of saying a equals 1. So you'll notice in this case I don't have f of a, in other words f of 1. So I'm going to start by plugging in 1 plus 2 times 1 squared comes out to be 3 squared, which is 9. When I do f prime of x, the derivative of the expression 1 plus 2x squared, you're going to use the chain rule. Derivative of the outside drops the 2 down in front and reduces my power to be to the first. Derivative of the outside, keep the inside the same, multiply by the derivative of the inside. Okay, so again, derivative of the outside, keep the inside the same, multiply by the derivative of the inside. So as I start to plug into this, I'm doing f prime of 1. This becomes 2 times 1 plus 2 times 1 times 2. If I clean that up, that's basically 4 times 3, and that comes out to be 12. So now I'm left with, once again, L of x equals f of 1, because our a value is 1 this time, plus f prime of 1 times x minus 1. And once I plug in the values that we calculated, this becomes 9 plus 12 times x minus 1. And again, I now have the equation of my tangent line. That model, L of x equals f of a plus f prime of a multiplied by x minus a, is going to be an extremely important equation, especially in this unit when we deal with approximations.